Okay, so last week we were counting the number of numbers that are co-prime to n in this set z/n. So we saw that out of n, this is the density of numbers which are co-prime. Right? The density is basically product of 1 minus 1 over p, where these p's are the distinct primes dividing n. Any questions here? Okay, so the proof we gave was by showing that this function phi, this Euler's totient function, is multiplicative up to co-prime arguments, and from that it follows quite easily. Second, an alternative proof was suggested by inclusion exclusion, right? That also can be done. Once you have this expression, it will be easy to see or easy to interpret this product 1 minus 1 over p by this inclusion exclusion principle. So what alternate proof is by so this inclusion exclusion principle will give you, did we do that somewhere? When, for example, we calculated this phi of p square by the first step of inclusion exclusion, we said that you just look at the complement, right? So p square minus the number of numbers that are that share a factor with p square. So instead of p square, if you had p times q, where p and q are different primes, then you could say pq minus numbers which share factor with pq, which will again be in two ways. Either it shares p or it shares q, right? So that will be the first step of inclusion exclusion. So how many numbers share factor p? That is pq by p, right? So that's q, and symmetrically the number of numbers that share factor q is p. So it's the opposite, and that's how you can write this expression down. So you will get phi of n to be sigma. So how many prime factors were there? I think let's write that. So say there were L prime factors, P1 to PL. So inclusion exclusion will be over all the subsets of 1 to L, and the count here will, if you recall how inclusion exclusion works, you will get this. Okay, so for example, when you take I to be empty, in that case size of I is 0, so that positive sign you get n by 1. So that's like taking the complement of the problem. So you are now starting with n, then there will be a minus, and n minus, now the minus term will be the first step of inclusion exclusion. So you will get there n by p1, then n by p2 dot dot n by pl with negative signs. Right? So sigma n by pi, that's the I singleton case. and then you take I to be doubleton, and then I to be 3 elements, 4 elements, and dot dot L elements, right? So you get this whole expression. And what is the interpretation of this summoned? What is this summoned doing? I mean, without the sign. What is n by p1, for example? It is what? Yeah, n by p1 counts those numbers which share p1 as a factor. But the problem is it may share many other things. But it definitely share p1, right? So that number is n by p1, which is why you need inclusion exclusion. So you can, if you don't understand this, you can go through this expression again. It's a quite straightforward application of inclusion exclusion, and then you can compare that these two red expressions are the same, right? So what we got by in the corollary is the same as what we have written now. And there is another way to write this. So this can also be written as sigma mu d times n by d, where d is a divisor of n, and where mu is what is called the Mobius function. So Mobius function is okay. So the definition is essentially it is -1 to the, what's the notation? -1 to the r if k is equal to product of r primes. With each prime appearing exactly once. So p1 times p2 dot dot pr. If k is of that form, right, like it was in this denominator, you had product of pi's. So if d is of that form, then it gives the correct sign, which is, this is the sign, -1 to the number of primes. Okay, that's the motivating case of mu that we are interested in. Everything else it sets to 0. So it's 0 if otherwise, basically. Okay, is that clear? So if k is just a product of primes, then it is plus minus 1. If it is not a product of primes, which means that there is some prime which whose square divides, for example, then mu of p square is 0. And just to be clear, for 1 it is 1. Okay. So this is not much. We just wanted to introduce this function, and you can see that what we have written at the top, it survives, mu survives only for square when d is product of primes, and then you get exactly this expression. Exactly the equation, the expression on the RHS of the last equation, you get exactly that. Okay, so there are 3 ways to interpret phi of n. Is that clear? and you have seen two proofs. So Möbius function is also important in some discrete math questions, but let me skip that part. Let us move to other things, which will be more important. So the first thing is, now we can give, so okay, where was that? There was Fermat's little theorem that you had seen. Right, you had seen this proof that a to the p is equal to a, or a to the p minus 1 is equal to 1 mod p we have shown when p is prime. And we have seen that it doesn't work for composite numbers. When p is composite, it doesn't work. So now can you see how we will correct this problem with the function phi? In a to the p minus 1, what is p minus 1? It's phi of p, right? So we'll try phi of n, e to the phi n. And we'll recover Euler's theorem. So Euler's theorem says that for all a which are co-prime to n, a to the phi n is 1 mod n. Okay, so in particular, so this is true for any n, composite or prime. So if in particular, if you take n to be prime, then phi of n you know is n minus 1, so you recover Fermat's little theorem. Okay, so this is the generalization of FLT. How do you prove this now? How did we prove FLT? We started with this set, which is basically scaling by a of all numbers. So what will be the analogous set now? Sorry? Zn star, yeah. So now instead of going over all the numbers, basically here also we went over 1 to p minus 1, that is Zp star. Now you go over Zn star, which will work all the time for any n. So consider or redefine that S to be A times B, where B is in Zn star. So in other words, take all those numbers B that are co-prime to n and scale it up by A, multiplied by A. And of course, we are only interested in Z slash n, so when you multiply by A, you also reduce mod n, right? We are working in that modern arithmetic. So ultimately, everything is between 0, 1, dot, dot, n minus 1. Okay, and then what did we do in the old proof? So then, if you recall, we considered the product of these numbers. So now what is the product of these numbers S in S? Right, you are interested in this product, of course, always mod n. So in every number, the small s, a is appearing, right? So in the product, how many times will a appear? Phi of n, right? So e to the phi of n is now coming up, which is good with respect to what the required equation you want to prove for the theorem to be proved. And what are the other things? The other things are these product of these b's, which is what? So these are all the b's in Zn star, right? So let's that we get directly. We bring e to the phi of n outside, and then we have product of b's in Zn star. Okay, so that is one side. What's the other side? How did we finish the proof earlier? So these s, small s, we have to prove something about them. Which is that every s can it share a factor with n? No, right? Because small s is basically a times b. If it shares a factor with n, a is already co-prime with to n, so then b has to share a factor with n. But b is also co-prime to n, so it's not possible. So this small s is actually in Zn star. And the other property is that if you take b and b prime different, then a times b and a times b prime are different. Right? So for different residue values b and b prime, scaling by a will give different results. This we have shown before. Basically a is invertible, so you can just divide by a both sides. So which now gives you the property that actually scaling by a is just permuting the elements of S. So hence we get this product to be also equal to product of all B's, which implies what? Yeah, so every B is co-prime to n, so product is also co-prime to n, so you can divide both sides and you get a raised to phi n is 1. Okay, as claimed. Any questions? So basically the counter example we had n equal to 4. Now you should look at a to the phi of 4, which is a square. So a square will be 1 as long as you take a to be co-prime to 4. If a shares a factor with n, then there is no result. But as long as a is co-prime to n, then this behaves in the best way possible. Any questions? Okay, so let's move to linear systems again. So where were we in the linear equations? So when we saw how to solve linear equations mod n, we could handle one equation. Right? What if you have two equations? So A1x congruent to B1 and A2x congruent to B2. What do you do then? Right, that we have not solved. So it's time we solve that. So so how do you solve A1x congruent to B1 and A2x congruent to B2 mod n? Both are mod n, and you want a common solution, right? So same x, which should satisfy both the equations. So what you have learned is that you will try to invert A1. Right? If you invert A1, then x is B1 divided by A1 mod n. And second thing will give you B2 divided by A2 mod n. So, but there were these cases that maybe A1 shares a factor with n, and then there were many solutions. Right? In the unique solution case, you just have to find one solution and check whether other equation satisfies that. But if there are many solutions, then you have to find all those solutions and check whether one of them satisfies. So that can be done algorithmically, but the question is, when can you guarantee a solution, and how many solutions are there for these two equations? So one bad example is, suppose you have first equation x congruent to 1 mod 2 and second equation is x congruent to 2 mod 4. Is there a single x which satisfies both these equations? Why not? Right, because the second equation, if it is true mod 4, it also has to be true mod 2, because 2 divides 4. Or you can make it 6 to make it more interesting. So 2 divides 6. So hence x has to be congruent to 2 mod 2 also. But the first equation says that x has to be 1 mod 2, so there is a contradiction. Right, so this leads to a contradiction. So contradiction means that there cannot be an integral x. So you want to understand why, I mean, looking at the equation, when will it be feasible, when will it be infeasible, right? So what do you think is the feasibility criterion? Actually, I should have made it more general. Maybe I made a mistake. This should have been by a different number. So A1x congruent to B1 mod m. So that is the first equation, and this is the second equation. Yeah, so not only are there two equations, but there are also two moduli. Okay, and then it becomes complicated. I mean, individually you can do that A1 inverse mod m, A2 inverse mod n thing. But how do you know whether there will be a solution or not? What is the feasibility criterion? So, since there can be problems when m and n are, so here I can make it slightly more interesting. Okay, I can put again the first modulus is 4, the second is 6. They have a GCD of 2. So when you look at the two equations mod 2, you see the contradiction. Right, so the problem happens when m and n share a factor, when the GCD is not 1. So let us assume that they are co-prime, then what happens? So m comma n greater than 1 creates a problem. What if they are co-prime? What do you think? If you have a system where you have two equations where m and n are co-prime, will there be a bad case? Can there be A's and B's so that there is no solution? Well, of course, there can be A and B's. There could be this, there was this problem, right? Even in a single equation, if A1 shares a factor with M, in those cases, B1 can create a problem. So that is one thing. But suppose A1 and A1 is co-prime to M also, and A2 is co-prime to N also, right? So let's go to that case. So further, AIs are 1. That is, we are looking at the equation x congruent to B1 mod M and x congruent to B2 mod N. Okay, so now individual equation there is no problem. What about this these two equations together? Can there be B1, B2 such that there is no common x? Okay, you haven't seen this then. So then we'll show that there is always an x, and there is a fast algorithm to find this x. Okay, so this is called the Chinese remainder theorem. From around 300 AD. So it's an old theorem. What it says is that this x, a unique x, exists. Or let me say like this. So an x exists moreover x mod mn is unique. Okay, so remember that m and n, we should see that maybe here. M and n are unique, co-prime. So in the following, we are assuming m and n to be co-prime. In that case, there will be an x such that x is B1 and B1 mod m and x is B2 mod n. Moreover, it will be unique if you look at its residue mod the product, which is Mn. Why do we need this? Why do we have to say that mod Mn it is unique? Is it unique without mod mn? Why not? Yeah, so whatever x you find, let's say x0, notice that x0 plus mn is also a solution, because mn is 0 mod m and mn is also 0 mod n. So adding multiples of mn still will be a solution of this simultaneous linear equation. So that is why you have to, I mean, there are infinitely many solutions. So to make those infinitely many solutions unique, bring it to 1, you have to say mod mn, and then it is unique. So this will need a proof, of course, this is not obvious. So how do you think you will prove it? Let me call this the first theorem. We will prove a more general form after this. Yeah, how do you specify this x? Yes, that's a brave attempt. So he is doing it because of this proof, right? We showed that there is a bijection psi from Zm star cross Zn star to Z slash Mn star. So there the map was this, A comma B was mapped to Na plus Mb, right? So let's try to do the same thing. So except that there is no star now. So A comma B will be mapped to something mod Mn, and here you can recall the previous expression. So previously psi A comma B was Na, so An plus Bm. So can we use the same psi here with this different domain also? In fact, let's keep this B1, B2 because that's our new notation. So it's B1n plus B2m. Yeah, so the thing is that what did you want to solve? You wanted to find an x such that x is B1 mod m and B2 mod n. Right? If you use this function, I mean the one which we used in the previous class, B1n plus B2m, what is it mod m? Mod m, it is B1n. It is not B1. Right? So this function will not work. So how do you change this function so that it becomes B1 mod m? This cannot be used as x because it's there is a difference in a factor. So instead of B1, it's giving you B1n mod m. How do you change it? Exactly. So this extra factor that it is giving you, n, you basically remove it, but you cannot truly remove it. You cannot just say that I will use B1 plus B2, right? Because if you use B1 plus B2, then what is B1 plus B2 mod m? Then it is something arbitrary. It doesn't have anything to do with B1 then, right? So if you remove n and m, then your whole approach is doomed. So you have to somehow remain close to this expression. So you have to keep n and m. So what you do is you multiply n with another integer, which is this n inverse mod m. So let's do that modification. So to correct psi, we redefine psi prime as, so psi prime b1 b2 will be b1 times n inverse mod m plus b2 times m times what? Yeah, the symmetric thing, so that will be m inverse mod n. Right, so it's a more complicated expression. If I gave it to you directly, you will not believe that this is what will work. But this is the reasoning, that we are slightly modifying the first construction. And then you just easily check that this thing, if you do mod m, right, then the second summand goes away because it's a multiple of m. And the first summand is n times n inverse, which is 1. So you get b1. And symmetrically, you get b2 mod n. Because now the first summand is killed and the second summand becomes b2 times 1. Is this clear? So which means that x has solution psi prime. Okay, so it's amazing that you were given these general looking numbers x b1 m and b2 n, and still we are able to give a closed form solution which will work for both. Is this fine? Okay, so right, so what did we get at this level of bijection? We have a map psi prime, which for every pair b1 b2 will map it to a number given by that formula, by that expression, and then reduce it mod mn. Do you see that psi prime is a bijection as psi was? So bijection would require you to prove that psi prime is a valid map, which it is. You check that, then you have to show that it's an injective map, which again will be a similar proof as for psi. And third will be that it's a surjective map, which again will have a similar proof. Okay, so all these three things will actually follow for psi prime as well. Psi prime is a bijection. Okay, so we have constructed another bijection, but what is the difference between psi and psi prime? Yeah, the domain and the range are different, right? These are different sets. So this psi prime is on a bigger set. And it can be sometimes a much bigger set. It's not Zm star, it's Zm, the whole Zm, and similarly whole of Zmn. So these are really different algebraic objects. Okay. And this means that for any B1, B2, we will have this X yeah, and it's surjective also. So for every X, you will have this B1, B2, which is actually the easy part. So all that remains is to show that it's unique. Suppose X and X prime are both roots, are both solutions. So then what happens? Actually, this also is covered, right? This when you will show that psi prime is injective, it will imply that this X is unique. So I don't need to show this. It's actually implied by the above. This implies that since psi prime is injective. So two different yeah, I mean two different x's, like x and x prime, cannot have the same B1, B2. That's the trivially follows from this. Any questions? That completes the theorem. So now you can go back and using this proof, which is also an algorithm, because it only needs you to compute inverse. Inverse again can be computed by Euclid GCD or extended Euclid GCD. So this is actually an algorithm. So this algorithm will give you the unique X, and which you can use as a subroutine to solve any system of linear equations, mod anything. Is that clear? So you can implement all that as an exercise. Set of modular linear equations can be solved efficiently. Okay, this is what we have learnt. And all we are using is inverses and GCD computations. Clear? Okay. So let's make this more complicated. If you think this was easy. So now well, maybe I should have given the exercise after theorem 2, because I have shown you, I've shown here only how to solve 2 equations. But what if you have 100 equations? Yeah, actually that you can do by using this repeatedly. If you have 3 equations, then you first solve the first 2, and then use that to solve the third. But okay, I can give that compactly now. So let N1, N2, Nk be co-prime, be mutually co-prime. Integers. So mutually means that any pair you take Ni comma Nj, it's co-prime. GCD is 1. Then the system of linear equations x congruent to Ci mod Ni for all I 1 to k. Okay, so x, so C1 to Ck can be anything. There is no condition on them. The condition is only on the Ni's because we want them co-prime. So for any Ci's, you can uniquely find x, that is C1 mod N1, C2 mod N2 dot dot Ck mod Nk. Has a unique solution x up to what? Unique solution x modulo product of these Ni's, right? And can be found efficiently. That's the part I have left as an exercise. But it's good to state it as a formal theorem. I will not prove this. I'll just give you the idea for basically this psi prime. Right, psi prime here we had defined as B1 n times n inverse. So similarly, psi prime for C1 dot dot Ck should be what? C1 times N1 times N1 inverse, but modulo what? So in the previous case, it was just N inverse mod. Sorry, it was M. Yeah, I'm messing it up. It was the opposite. It was for B1 you used N2 times N2 inverse. So here it should be what? It will not be this. It will be something else which I am calling N1 times N1 inverse. Where N1 is basically Ni I will take to be the product. Actually, I have to define many things. Let's take big N to be the product of everything, and Nj to be this. Okay, so big N is the product of all the numbers, and big N sub j is all the numbers except the jth one. So I divide by n sub j, small n sub j. So if you are confused, think of the case k equal to 2, right? So there you had only small n1 and small n2. So for the first one, for j equal to 1, we actually used small n2, and for j equal to 2, we use small n1, right? So this definition is consistent with that, and that's what we will write here. And let me just make it compact. Is that clear? So that's the expression I have given you, and then it's a routine exercise to check that it works. This is the generalization of k equal to 2 to any k. So it takes this Cj remainder, multiplies it with all the moduli except the jth one. With respect to that, it can now take the inverse. Because big Nj and small nj, they are co-prime. And then you sum it up, you will get the unique x. Is that clear? So proof is exactly the same once you have the psi prime maps set up properly. And algorithm is also the same because you just have a number and you want to take its inverse. So it will again be possible by the same subroutine called extended Euclid GCD. After that, you just multiply and add. Okay, so now this should give you the complete solution of any system of linear equations, any moduli, arbitrary moduli. Is that fine? Okay, so that should complete modular arithmetic. So you can ask questions about anything in modular arithmetic if you have. Next class we will do some applications of this, especially in cryptography. Some very simple applications where these things are used. Okay, so since you are not asking questions, I can move to an intermediate topic before the application, which is density of primes. So the basic question or the basic objects you saw in all the previous calculations was numbers which are prime, right? When n is prime, then the best things happen. And the other, which are the composites, they just follow those rules in a systematic way. So the question that appears is how many primes are there? Okay, you are interested in this function pi of x, let's call that. So pi of x counts the number of primes between 1 to x, or primes which are less than equal to x and positive. Okay, so that's the density function for prime numbers. The first question is pi x a growing function? Or after a point will it stabilize? Will it become constant? It will keep growing. What is the proof? Sorry? Yeah, what is the proof of that? I think we saw that proof in the first class. Okay, so that much you have learnt already, that pi of x tends to infinity. Right, which means that there are infinitely many primes, so then it is a natural question to study the density of primes. So what is pi of x divided by x? right, in any interval, in this up to x, how many primes are there as a fraction? What's the density of prime numbers? This is important because if this density is extremely small, then you will not be able to find useful primes in practice for any of the applications. Right? Suppose you want a 1000-digit prime, and for 1000 digits, suppose there are only 10 primes available. So how will you find them? There is no formula for primes. So you have to go over all 1000-digit numbers, which is like 2 raised to 1000 or 10 raised to 1000, out of which only 10 you will find, right? So which is a very, very bad algorithm. Again, you won't be able to find them because they can be anywhere, those 10 numbers. So which is why it's important that the density has to be extremely good. So do you know what this is? Okay. Can you prove that? So let's prove that. So pi x over x is around 1 over log x. Okay, that is the density of primes. In other words, 1 to x, there are around x over log x prime numbers, which is extremely good. Okay, because again, this is saying roughly that for 1000 digits, if you randomly picked an integer which is around 1000 digits, then the probability of it being prime is what? 1 over 1000, right? Which means that if you pick 1000 many random numbers, then one of them is prime with a very good chance, right? So you just have to sample integers and you will get prime numbers. So that is why this density is extremely important. It makes everything we have done practical in the applications, because you can find primes and then you can build your designs. So how do you show this thing? So let us just show an estimate. Which I think is, the proof I will present is mainly due to Erdos from the 1930s. Okay, the key thing is that it's very elementary. So in the next class, now I think it's over. So maybe in the few minutes of the next class, we'll be able to finish this proof. It's very elementary and it's useful in computer science because you don't need very precise estimates. It will be enough to just prove this. For all x greater than or equal to 5. Okay, so there will be we'll see a quite elementary proof that number of primes between 1 and x is between x by log x and 5x by log x. Okay, so this is a simple estimate that Erdos gave. So let me just list the lemmas that we will need and we'll sketch them next time. So this needs 3 simple counting lemmas. So you have seen many counting methods when we were doing combinatorics. So just from there we will use some simple properties of binomials which will imply this density estimate of Erdos. So first lemma is, so let me call it lower bound. So this lemma will say that 2n choose n is large. Okay. So 2n choose n, it will say is at least 4 to the n divided by 2n plus 1. Okay, so it grows exponentially and exactly this way, 4 is to n. What is the proof of this? This has a trivial proof. You look at the binomial sum 1 plus 1 to the 2n, right? That is 2 raised to 2n, 4 raised to n. So sum of all the binomials is 4 raised to n, and the number of binomials is 2n plus 1. And this guy seems to be happens to be the maximum, right? So it's more than the average. So that's the simple lower bound. Second is, now it will connect 2n choose n with primes. Basically, it will look at what are the prime factors of 2n choose n. This will be trickier. So if a prime power, let's say, if prime power p raised to v divides to 2n choose n, then that prime power has to be small. Okay. So p is a prime, v is some exponent. If p raised to v is a factor of 2n choose n, notice that 2n choose n is a very big number. It's like 4 raised to n. Right? So prime could also have been as big as 4 raised to n, but it cannot be. This lemma says that it's at most 2n, which is ridiculously small compared to the value of 2n choose n. Right? So this is a tricky lemma. We have to see the sketch next time. And third lemma is I'll call it the upper bound. Which says that product of primes up to n is not too large. Okay. So it says that if you multiply all the primes, then it's at most 4 is to n, which is the least interesting lemma, because this is kind of going the opposite way. It is showing that there are fewer primes. Okay, but we will need lemma 3 to give both sides of the estimate. So the interesting things are lemma 1, and most interesting is lemma 2. So using this, the Erdos estimate can be proved. We'll do that next time. Okay, you can ask questions if you want.